Good day, students. Today we'll delve into the world of X-ray diffractometry, a powerful technique widely used in material science, crystallography, and various other fields. In this lecture, we will explore the theory behind X-ray diffractometers, understand how to load samples effectively, and dive into result analysis. Let us start with the theory. X-ray diffractometry is based on the principle of X-ray diffraction, which allows us to determine the atomic and molecular structure of crystalline materials. This technique relies on the interaction of X-rays with the crystal lattice of a material. When X-rays strike a crystal, they are scattered by the atoms within the crystal lattice. This scattering occurs at specific angles determined by the arrangement of the atoms in the crystal. The scattered X-rays interfere constructively, creating a diffraction pattern. The Bragg equation given by the n lambda equals to 2d sine theta is fundamental to X-ray diffraction. Here n represents the order of the diffraction. Lambda is the wavelength of the X-rays, and d is the spacing between crystal planes, and theta is the angle of incidence. By measuring the angles at which X-ray diffraction peaks occur, we can determine the d spacing and subsequently the crystal structure. X-ray diffractometers use a monochromatic X-ray source and a detector to measure these diffraction angles. The resulting data is called an X-ray diffraction pattern or diffractogram. Now let's discuss how to load samples effectively. Proper sample preparation is crucial for accurate results. Samples should be finely powdered to ensure that all regions of the materials are represented in the analysis. This powder is then carefully packed into a sample holder or sample stage. The sample holder must be made of a material that does not interfere with the X-ray diffraction, often using materials like glass or quartz. It should securely hold the sample in place and allow for precise positioning. Minimize air gaps or voids in the sample, as they can lead to inaccurate measurements. Pressing the sample with the hydraulic press can help ensure uniformity and reduce the presence of voids. Moving on to sample analysis, the output of XRD is typically a diffractogram, displaying intensity of the y-axis and diffraction angle theta on the x-axis. Peaks in the diffractogram correspond to the angles at which XRD occurred. Identify the peaks in the diffractogram and determine their positions. These positions correspond to the d spacings which the crystal lattice. By applying the Bragg equation, you can calculate the crystal structure and lattice parameters. Compare your experimental diffractogram to reference patterns from known crystal structures to identify the material's crystalline phase. Additional analysis can involve quantifying the relative amounts of different phases present in a sample and assessing the crystallinity or degree of crystalline disorder. In conclusion, X-ray diffractometry is a powerful tool for investigating the atomic and molecular structure of crystalline materials. Understanding the theory, sample holding, and skilled result analysis are crucial for obtaining meaningful data. Thank you for your attention. I hope this lecture has provided you with insights into X-ray diffractometry. If you have any question, please feel free to ask. Thank you.